In previous lessons, we were working with simplifying radical expressions. We are going to continue on with the idea with not only our values being there, but also with some variables. So let's go back to what we've been working with previously. If we have the square root of 60, we always ask ourselves what's the largest perfect square factor that belongs with 60. 4 would be the largest perfect square factor, and we know 4 times 15 is 60. So using 4 as the perfect square, the square root of 4 is a value of 2. The square root of 15, there's no perfect square factors for 15, so we leave it as is. So the square root of 60 simplifies to 2 square roots of 15. Our second one, the square root of a negative 125, we said anytime there was a negative underneath the radical, we wanted to rewrite it. So it was a positive times a square root of a negative 1. Then we ask ourselves, again, like we did before in the last problem, are there any perfect square factors associated with this value, 125, which we know is 25, and 25 times 5 is 105. The other important piece is the square root of negative 1. We know that the square root of negative 1 is designated being represented by I. So we're here. We know that 25 is the perfect square, so the square root of 25 is 5. Then we have I times the square root of 5. So again, the square root of a negative 125 simplifies to 5i squared of 5. A couple of items from the past, again, simplifying the radicals. So here we've got negative 5 times the square root of 24. Again, we're going to ask ourselves perfect square factors of 24. That would be 4. 4 times 6 is 24. We know the value of the square root of 4 is 2. And we know negative 5 times 2 is 10. So negative 5 square root of 24 simplifies to negative 10 square root of 6. For our next problem, we've got the square root of negative 27 sevenths. And within the radical, we know that other than 1, 27 and 7 don't have any common factors. So instead of having it written as 1, we're going to write it as 2, the square root of the numerator compared to the square root of the denominator. Like we've done previously, whenever we have a radical with a negative underneath it, we want to rewrite it so it's the square root of a positive times the square root of negative 1. So we have the square root of 27 times the square root of negative 1. We know that the square root of negative 1 is denoted by I. And still ask yourself, like we've done previously, what perfect square factors does 27 have? 9. 9 times 3 is our 27. So we know that the square root of 9 times the square root of 3 times I is in the numerator, the square root of 7 is in the denominator. The square root of 9, that's our perfect square, that has a value of 3. So in our numerator, we've got 3i times the square root of 3. All that's being divided by the square root of 7. So the numerator is simplified. Now the denominator. The denominator has a radical. And when we're simplifying radicals, we know that we want them to make sense. We need to rationalize them. So we don't want a half square root in the denominator. We need to multiply this by a value of 1 to undo that square root in the denominator. So we're going to multiply by the square root of 7 in the numerator and the denominator. Because again, that's a value of 1. We're not changing the value of the expression, just how it's written. Again, with your fractions, you multiply across things with in the boundaries of the radical sign, right? The square root. We can multiply those together, and numbers on the exteriors can get multiplied together. So in our numerator, we're going to have 3i times the square root of 21. Our denominator is going to be the square root of 49, which we know is a perfect square, and that has a value of 7. So our final simplified result should be 3i squared root of 21 divided by 7. Now we were simplifying radicals that just had values underneath them. We know that's not always the case. We could have values and we also could have variables and still be able to simplify them with the same methods. So let's try a few of these, practicing and extending upon what we've done previously. So here we've got the square root of 50x squared y to the third. So we've got our square root, which is also known as a radical, and we know the index that's implied here, the number, right? It's usually here for the radical is a 2. So we try to write things as perfect squares. Something times itself, right? That means it's a power of 2. So let's take this in pieces. Let's look at the value of the square root of 50. Does that have any perfect square factors? Yes, it does. 25 times 2 is 50. 25 is the perfect square. So I could take that square root of 50 and write it as the 25 and 2. Now x squared, that itself is a perfect square, so we can leave it as that. And y to the third has a perfect square within that, y to the second power, y squared, times y. I'm trying to write all of the elements as perfect squares because we know the value for those. So my perfect squares are 25, x squared, and y squared. We know we have the square root of 25 that has a value of 5. The square root of x squared should be x, and the square root of y squared would be y. So those are now in the exterior radical. What's still left in the interior? 2 and y. So the square root of 50x squared y to the third simplifies to 5xy times the square root of 2y. So we take a look at our next problem, again within the radical, underneath the square root. Try to write things as perfect squares. So 15, does that have any perfect square factors? No, it does not, so we'll leave that as is. X to the fifth, does that have any perfect square factors? Well, x to the fifth means there are 5 x's, so I could write them in pairs, right? Because that would be a perfect square. So I could have x to the second times x to the second times x. There's 5 x's there. Y to the sixth, well, that would have 3 pairs of y to the second. So like in our last problem, we just list out our factors involving as many perfect squares as possible. So looking here, let's see what would be a perfect square. X squared, y squared, y squared, y squared. So what will now be left to work with? Well, we know the square root of x squared is x. We'll have another x. The square root of y squared is y. I'll have a y, and I'll have a y, with my 3 on the exterior of the radical. What's left on the interior would be 15x. Now this isn't fully simplified yet because look, we have all of these pieces on the exterior of the radical, and we could simplify that a little bit better. We have 3. We know x times x is x squared, and y times y times y is y to the third. So we now have 3x squared y to the third times our radical of 15x, or you could refer to it as the square root of 15x. Now we know that we've been working on simplifying radicals because they appear a lot of times when we're solving, so that means we've also had to do operations with them. So we've done some of these in the past as well. We talk about simplifying the expressions, and we can see we've got some multiplication with these radicals happening. So one way we could simplify this, because we're multiplying the radicals, is we could take, again, what's underneath the radicals and multiply them together. 10 times 20, that would be 200. So we have the radical of 200, or the square root of 200, if you prefer to call it that. Now, like we've done before, does it have any perfect square factors? 200 comes from 100 times 2, and 100 is our perfect square. And we know the value of the square root of 100 is 10. So the square root of 10 times the square root of 20 is 10 square root of 2. Another option is to simplify each radical individually and then multiply your results. So 10 does not have any perfect square factors. We could leave that as the square root of 10. The square root of 20 has a perfect square factor of 4, so we could rewrite that as the square root of 4 times the square root of 5. The square root of 4 has a value of 2. And now we can see we've got some simplifying to occur. We've got the square root of 10, the square root of 5, that would be the square root of 50. which has a perfect square factor of 25. 25 times 2. The value of the square root of 25 is 5. So now I've got 2 times 5 times the square root of 2. Well, that results in 10 square root of 2 as well. Both of those values, both of those, I shouldn't say values, both of those methods of simplifying the radicals are valid, and they'll leave you with the same result. So whether you choose to multiply right away underneath the radicals and simplify, or simplify each radical individually and follow the order of operations, you'll still have the same result. The only time you would not want to do that is if you saw a negative underneath the radical, because that would impact your results. Simplify each radical individually, like in our method 2 here, and then see what you'd have for your final answer. All right, we've done things like this in the past. 3 square roots of 8 times a negative 2 square roots of 5. So we could see we've got some values on the exterior that we can multiply together. Values underneath the radicals could get multiplied together. 3 times negative 2 is negative 6, and 8 times 5 is 40. So at this point, you want to ask yourself, does it have any perfect square factors? The square root of 40? Yes. 4 times 10, so we'd write that as negative 6 times the square root of 4 times the square root of 10. We know that the square root of 4 is 2, so negative 6 times 2, that would be negative 12. We've got negative 12 square roots of 10. Now we have another way that we could have simplified this as well. We could have simplified each radical individually and then see what happens. So if you did it that way, you'd have 3 times the square root of 4 times the square root of 2 times negative 2 square roots of 5. We know the square root of 4 is a value of 2, so 3 times 2 is 6, so we'd have 6 square roots of 2 times negative 2 square roots of 5. Because we've got these 3 factors on the exterior of the radical that can get multiplied together, and 2 underneath the radical that can get multiplied together, that will also give us our negative 12 square roots of 10. So similar to what we're doing for the values, we can do the same thing when it involves variables. To look at this problem, I could look at the individual radicals and ask myself if I would like to simplify them first, looking for perfect square factors, or would I like to, instead of having 2 radicals, write it as 1 and go from there. Personally, I would like to do it the second option, write it as 1 radical, and seeing how I can break that down into perfect square factors. Well, 15 doesn't have any perfect square factors, and neither does 6. But I know 15 comes from 5 times 3, and 6 comes from 3 times 2. I can write those and see if I can make some perfect squares out of that. X squared, well, that's a perfect square, and x to the 5th, I can write that as a perfect square as well, right? X squared, that's x to the 4th with 1 more x left over. So I have 3 perfect squares here. Do I have any others? Well, if you notice with your values here, we've got 3 times 3, that's a perfect square, so that will help us simplify that radical. We got 1, 2, 3, 4 perfect squares. So we know the square root of 3 squared, or 9, is 3. Square root of x squared would be x. X, x, those are now on the exterior of the radical. We could see what's left on the interior. We'd have a 5, a 2, and an x. So now we can continue simplifying. On the exterior, we would have 3x to the 3rd. On the interior of the radical, we would have 10x. 10 does not have any perfect square factors, therefore this would be my fully simplified result. Again, when working with your radicals, we've seen things like this pop up, in particular when we've been solving our quadratic equations, right? So let's see what we can do from here. We can see that we've got the radical of 20, and 20 has a perfect square factor of 4. So we could write that as the square root of 4 times the square root of 5. And we know that the square root of 4 has a value of 2. So I'm now at 6, right and left, 2 square roots of 5 over 2. This is not fully simplified yet. To keep simplifying, we have to know that we're taking each of these elements and dividing it by 2. So let's think of that separately. We've got 6 divided by 2, right and left, 2 square roots of 5 divided by 2. Well, 6 divided by 2, or 6 halves, that's an equivalent of 3. And 2 square roots of 5 divided by 2, well, we've got a common factor of 2 that we could divide out, so that means we're just going right and left the radical of 5. Therefore, we'd have 3 right and left, the square root of 5 for our 2 results. If this was a quadratic equation, right, that would have our 2 answers, 3 minus square root of 5 and 3 plus square root of 5. Here we're just simplifying the expression. So we start off again with 6 right and left, the square root of 20 divided by 2, simplifies down to 3 right and left, the square root of 5. Let's try one more. Here we have negative 10 right and left, the square root of negative 40 divided by 6. How can we simplify? Well, your eye should go to that radical first. And we know that whenever we see it being negative, we want to rewrite it as a positive times the square root of negative 1. So we're going to rewrite this as the square root of 40 times the square root of negative 1. This is nice because 40 has a perfect square of 4. 4 times 10 is 40. And we know the square root of negative 1 is denoted by I. So for simplifying, this would be 2i times the square root of 10. Now, we're supposed to take these two pieces, right, and divide them by 6. So I can compare negative 10 6 and divide out common factors. And I can compare these two, 2i squared root of 10 6, and divide out common factors. Well, 10 and 6 has a common factor of 2, so that would simplify to negative 5 thirds. And here, we can see that with the exteriors, we have a common factor of 2 again, so it would be I squared root of 10 over 3. They both have a common denominator of 3, so instead of having it as 2 separate, we could write it as 1 as negative 5, right and left, I squared root of 10 over 3. Now it's your turn to practice. Again, we're building off of skills that we've done before with simplifying our radicals and extending it by working with some variables underneath the radicals. So you're going to do some practice work for Unit 9, Day 1. You should have jumbled answers on the back. If not, they are here to see if you're on target, simplifying each of those expressions to see what's remaining. Again, this is important because we've seen radicals show up a lot when we've been solving our equations, particular quadratics, and so it's important to have that skill to help us talk about the results, what they represent, and going forward how we can make some ties into that with our graphs.